welcome back from the break. Our next speaker is Silke Henkes from Leiden. Thanks.
Thank you very much, and I would like to thank the organizers for inviting me to this very nice meeting. This time I had to come all the way from the INI across the yard, where I'm currently one of the co-organizers of the SPL program. But my main base is and has been since 1 year now, Leiden University in the Netherlands. So what I would like to tell you about today is work which has gone on over the practically last 10 different years in many different places. Syracuse University, when I was at Aberdeen, Bristol University, and NC State. So I wanted to acknowledge all my co-workers over the years, especially Jen Schwartz and Kwame Liu at Syracuse University and Karen Daniels at NC State. And I'd like to acknowledge funding, including the lack of funding over many of these years. Especially the lack of funding, yes. So I don't think I need to introduce grammar materials to this audience. They're everywhere in geology, for example. One can do pretty scary things to doing solid liquefaction in an earthquake. That is on Earth anywhere. It might be anywhere else in the universe as well, including on Mars and who knows where else. Of course, grammar materials are also very cool, and one can hack M&Ms. And okay, I don't need to give you a history of this whole field, but what I'd like to talk about is also something which you, I think, seen before, which is the jamming transition. So the picture is, or the classical picture of frictionless jamming is that below a certain packing fraction, the system is unjammed, so it's not mechanically rigid, things might or might not be touching. With above jamming, things are mechanically rigid, have about a shear modulus, and there is one usually well-defined frictionless jamming point at either 64% in 3D or 84.2% in 2D. And so this has been summarized for years here. The jamming diagram started here by, in fact, Andrea Liu and co-workers, and yeah, everybody here, in fact, yes, and refined over the years. And I just wanted to say that something more recent, people have indeed tried to unify this with the glass transition paradigm, and in fact, in the infinite dimensional limit, one can do something. One has a feedback paradigm which can unify this as essentially two even limits of the same transition. However, this is not what I would like to talk about. What I'd like to talk about is most definitely not a glass, and despite people's best efforts, is probably not linked in any way to the theory of glasses, which is frictional jamming. So in frictional jamming, the phenomenology which you would have for frictionless jamming, which for this cut out, this would be stress on the y-axis, packing fraction on the x-axis, and then it's either jammed or unjammed with this line going slightly forward. Doesn't look like that. In fact, one gets new phases, which have been called shear jammed and fragile, and more than one jamming packing fraction, where one can get into this region by, I'm supposed to stay close to this thing, right? And so using shear, you can move away from this axis, and in fact, ultimately what's happening inside map packing is microscopically a Coulomb criterion, so individual contacts have a phi-like criterion if the tangential force is bigger or equal to the normal force, but it has never been clear over the years how this translates into a global failure criterion. And for example, as in the shear jamming criterion, where it's been used to use the percolation of force chains from one side to the other as a criterion of the jamming transition. So what I'd like to do is I would like to delve back into the microscopics of these packings, so microscopic stability to macroscopic stability, and try to see if we can gain a better understanding of what's happening in there. So very luckily for frictional particles such as these, this is interesting here. Yeah, okay. We can, in fact, look into these packings. So these are experiments of my colleague Karen Daniels, similar to the ones which are pioneered by the lab of Bob Behringer, that put elastic disks. So these are plastic discs between cross polarizers, and you can in fact see the stresses concentrating along chains here with this packing. So there's large ones here, small ones there, and you can see force chains and similar. So this is one tool of looking in there. And what I would like to do in this talk is to sort of dig into the nature of the frictional jamming transitions by starting from constraint counting. That is really interesting. Sorry, it keeps coming.
Because it's still on it's online.
Yeah, I know, and it's here, and I'm seeing it here, and this is in fact connected, and I don't understand what the problem is. Or we plug it back into there. It wasn't perfect, but it would do it, right? No, keep it in there. No, I want to. Where was it? Where's the connector? Yeah. I feel it's my projector actually. So I suspect it's the projector actually. It's just misbehaving, not anything else.
The spacing not in that one.
Or the cable. So we have it here, we have it there.
So that's the Zoom call. The Zoom call is working fine. It's the problem is the stuff in the room.
So we connected it. It was on mine. We connected it there, so neither of them is working. So it might be the cable, or it might be the projector. So we tried two connectors. That's not it. Sorry, we'll get there. Don't think so.
Do you think you could give the talk without slides?
No. Okay. What did you change?
Don't touch anything.
Yes, we can use this.
Yeah, okay, good enough.
Yeah, you can still advance on your screen.
Yeah,
This is a different Zoom participant.
Yeah.
Okay, so then you have subjects.
Okay, we'll continue like that then. And okay, it seems to be going away eventually. Okay, anyway, so let me very quickly go ahead now. So we're going to look essentially trying to see if you can explain any of this using the tools of rigidity percolation. I'll walk you through this bit by bit. So let me start by good old-fashioned Maxwell constraint counting. So the idea is, in particular for friction, let's start with frictionless jamming, that I have 2 degrees of freedom per particle, or d degrees of freedom per particle, and at the same time, every contact I do gives me a constraint, so I have a total of mz over 2 constraints in my packing. Then I can play a mean field argument and say I need to have at least enough constraints to stop my packing from moving. And this gives me the frictionless isostatic point 2D, which is 4 in 2 dimensions, and I should say this works empirically extremely well for frictionless jamming. So for frictional jamming, you can play the same game. You can say I have now 1/2 n times d times d plus 1, translations plus rotations. I have more force components. I have 1 times n dz because I have d independent. I get to that independent constraints per contact. So one, for example, one normal, one tangential in 2 dimensions. So if I solve this, I get the infinite frictional isostatic point, which is d plus 1. So for example, 3 in 2 dimensions. So empirically, fractional packings tend to fall into the range from here to here between 3 and 4. And so this empirically doesn't work, or it works in certain situations, but not well and not in others. So the question here is what's happening at this point. And so what's happening is, among others, that one might want to look at rigidity percolation. So rigidity percolation is, if you want, the non-mean field way of constraint counting. And so I'm going to explain it using the equivalent of frictionless jamming, which is incorporated in Lamant's theorem. So the idea is that I'm going to map my packing into a planar 2D graph, which looks like this. So just m edges and n vertices. And the Lamant's theorem says, for a graph with 2n-3 edges, the edges of G are independent if and only if no subgraph G prime has more than 2n prime minus 3 edges. So what that means is essentially, if I'm exactly isostatic, so you have 2n minus 3 constraints, which corresponds to the edges here, and I should say the 3 is because in this very careful counting, you take into account the global degrees of freedom, which means 2 translations and 1 rotations in 2 dimensions. If I'm globally isostatic, that's only possible if I'm locally isostatic everywhere, and I don't have redundant bonds somewhere in the system, because else that would make another part of the system floppy. So it has to be everywhere isostatic for it to be isostatic. And so it's a local generalization of the frictionless isostaticity criterion, with the 3 in here. So this has been looked at in simulations. For example, a group of Walter Weldenbroek and co-workers looked at this, and they found, in fact, something interesting. While this rigidity percolation on your classical triangular network or something like this is a second-order critical phase transition, if you take a jump packing there, frictionless jump packing, you get a block mean field jump transition. So it looks completely different in an actual jump packing than it looks in a classical network. And so this is one sort of supporting evidence that the frictionless jamming transition is indeed something block and mean field, which is significantly different from what you would expect generically in a network. And in fact, I would say, yeah, mean field tends to work for frictionless jamming. But the point is, for frictional, this doesn't work. And this is where I would like to go with this. So the first thing I wanted to say, one has to in fact slightly tweak this criterion, because in frictional jamming, you can have not only the contacts which are below the Coulomb criterion, but I can have also contacts which are at the Coulomb criterion and sliding. So for these contacts, which we call fully mobilized, in fact, what happens is that you do not have an independent tangential constraint. The tangential force is set by the normal force, and so you need to take out some constraints of your system. And if you do this counting, you take this out, you will get a different criterion, generalized as a staticity, where Z has to be bigger than B plus 1 plus a linear correction in the number of these contacts. And this here is old work, but about 10 years ago, we showed that, in fact, if you take this seriously, you can reproduce the phenomenology of frictionless jamming using this, including a density of states, which has a plateau with scaling, which goes linearly in the distance from other generalized isostaticity, and that this acts like a critical line of phase transition. So there is something there about that line, in fact. So what I'd like to do now is I would say, well, this was a very, very careful simulation, which isn't all that generic. So in a generic system, I want to look into this and understand why it might not be mean field. So what I would like to do is, in fact, generalize the rigidity percolation to include friction. And for this, I would like to introduce the 3-3 pebble game for frictional rigidity percolation. So the idea is that the pebble game is a way of enacting Lamant's theorem on a graph. I would like to modify it for friction by including the sliding forces and more degrees of freedom. So the idea here is I take my packing with frictional and sliding contacts, and I map it to a graph problem for every particle. There's 3 degrees of freedom. Every contact with friction provides 2 constraints, and every contact at the Coulomb criterion, every sliding contact provides 1 constraint. So it's a mapping between the packing and the graph problem. And I can then use what's called the pebble game. So it's a graph search algorithm to place these degrees of freedom onto the bond. So use the constraints to get rid of degrees of freedom, recursively using a rapid search. And this is good because it's not mean field, and it will allow me to disentangle which parts of the system are rigid and which ones aren't. And as you can see in the last step here, for example, in this one, part of the system is rigid and part of it isn't. So I'm going inside my packing to disentangle different pieces of it. So we first tested this some years ago now on a frictional sheared simulation. So it's a pretty standard kind of thing. It's a candle-struck interaction, which is harmonic in the normal direction and also harmonic in the shear direction until a failure criterion. And Lise Edwards' shear boundary conditions, we worked at constant volume with extremely slow shear down to 10 to minus 6, then similar packing fractions across the frictional jamming transition. So I wanted to say here, so you can look at this as a function of pressure, as a function of distance, visualized as a statisticity line. You can see the transition appear here. So these are all different system sizes and 3 different strain rates, but you can see as the strain rate decreases from 10 to minus 5 to 10 to minus 6 to 10 to minus 7, the region here, which is above jamming at high pressure, doesn't really change, but below jamming, this scales down with the amount of the strain rate. So this is viscous forces dominated. This is contact forces dominated, because we always have dissipation, in this case pair dissipation, just pair damping between particles. And if you draw this generalized statistic plot, what you can see is that it actually works relatively well. So these are by pressure identified rigid systems. These were the floppy ones. But if you zoom in, then you find yourselves is no mixed region across the transition. So it works reasonably well, but it's not an exact prediction if something is rigid or not. So if you now finally play this pebble game on these packings and decompose the system into pieces, what you get is you start with something like this. So your packing, here this is the rigid and the friction with the sliding bonds. After playing the pebble game, I get this, so I should say, mostly bonds I've been able to add in red. I get leftover pebbles corresponding to isolated particles and some non-isolated particles. And I also have some bonds I couldn't add, so redundant bonds. So just the fact that I have pebbles left and bonds left, this is beyond mean field counting. So for example, this is also a very obvious way of identifying rattlers in the system. When you decompose this and you find something interesting immediately, this is partially rigid. This is a system with gray, floppy regions and black rigid regions at the same time. And that's not an isolated situation, because if you do this systematically over a whole run, you see something like that. So this is in the region where I'm between jamming and unjamming and at constant volume. So currently this is jammed with high forces in the system, and it's rigid, as you can see in black. Then eventually it will unjam, and you can see in a moment that you also lose the rigid clusters when that happens. Yeah, so it's unjammed now, and the system is mostly floppy with small rigid clusters here, which are very far from system spanning. So you can do statistics on this, and what we find is something, and I want to qualify this a little. So it has the hallmarks at that system size of a second order transition, in particular in such a way that the cluster size distribution, which you can see here, is continuous. So you can see something parallel like appearing here in the transition region. And I want to really contrast this to this thing here. So this is the exact same simulation run in the exact same circumstances, but with a frictionless system. And you see there is a gap here. So there is a gap in cluster size between 100 and 1,000, which you just don't see here. These are significantly different from each other. So qualitatively different between frictionless and frictional. We can also do a limited amount of finite size scaling, which gives you the same thing. This has hallmarks of first order, hallmarks of second order, consistent here, the first order, with what Ellenbrook and Kohlberger found. And it's also these these rigid pieces aren't really figments of our imagination. Mechanically, they have a strong mechanical role, and you can do this by looking at the normal force or the pressure inside the cluster compared to the pressure outside of the cluster. And if you normalize this by the total pressure of that particular packing, you find that if you're below the transition, here, this is a fraction of the system inside the rigid cluster, you can see there's no difference, they both bear the same load, but if I go through the transition, the clusters bear all of the loads, so they stay here close to 1 here, and the floppier regions bear less and less of the load in the packing. And so these ultimately become what people usually call raptors in this community. So they bear less and less load, and they just become part of the pieces which are not bearing stress in the system. You can also look at another measure of rigidity, which is non-affine motion, using a couple of different measures, but they all in common show that the floppier regions have a lot more non-affine motion than the cluster regions, note the log scale on here. So there's a picture emerging from here, and it looks now slowly, I'll come back to this later, that it might be generic, that above the rigid, so that essentially the rigid clusters emerging out of the viscous background. So if you're below here, viscous forces dominate, and there's nothing going on with rigidity transitions. And at the rigidity transition, these things are emerging out of viscous background and then start to bear the load. So we then check this next on actual experimental packings of Karen Daniels. So we did basically the same thing. So this is a constant volume I set up, but it's quasi-static strain steps. So finite but small strain steps in the system. And then we do the same decomposition and also a couple other things I will tell you about in a moment. So first of all, here is the exact same movie as I showed you a minute ago, but now done on experimental packings. So on the left, you have the forces and contacts. On the right, you have the rigid cluster decomposition. And just like before, you can see the strong correlations between being jammed with high forces and then being unjammed with the rigid cluster being present. I should say the system for the experts, we are going through a shear jamming transition in this system. This is strongly hysteretic. Right, I'm pushing, I'm jamming, and I'm getting a rigid, expanding rigid cluster here. And once I reverse, it will all fall apart, and so will the rigid cluster. So, because some mathematicians, and I didn't mention it earlier, had raised questions about is 3 pebble games for these non-concentral forces, is this all mathematically off board? Yes, above board. If we use an extra method to check this, and in fact we use the Hessian matrix, so we can compute an effective dynamical matrix from these Candle-Struck interactions if you assume that the tangential motion is infinitesimal. So this, you can convert this to an effective spring as long as the thing is not sliding. If it's sliding, it has 0 tangential spring. So this is a piece of dynamical matrix for single contact, so it's not in global coordinates, it is normal, tangential, and rotational. Despite appearances, this makes a symmetric matrix, and I should say this is the limit of what the group of Focaccia has proposed as a Jacobian, which it becomes different once you go through an actual point where things rearrange, but if you away from that, this is identical. And so we identify rigid and floppy regions by very simply looking over all normal modes and looking where are regions where the motion means where motion of the thing is negligible. So then we have a criterion, and you can make certain this is a clean criterion and reproducible, but you can look at where does stuff not move. And if you do this, here you can compare these rigid regions compared to the rigid clusters we have just showed you. As you can see, they're very strongly correlated with each other between a rigid cluster and a rigid region. And so again, here we are jamming, then we are unjamming. So it's the same experimental data set.
Sorry, can you explain a little bit more in detail what's changing?
This is methods or experimentally?
In the experiment, so you compress, you said it's constant volume, then you add
so
pressure, and then what do you do?
It's a pure shear setup. So you compress in one direction, you expand in the other direction, and you do this in small steps and then measure. That's all it is. And she's
and then what do you here is the reconstruction of the network at different,
Yes.
at each cycle?
Between individual steps. So this is, we have several of these. So this is a full step where first shear in one direction, then shear in the reverse direction. And I should say there is an Airtable setup, so as minimized as one can for friction with the bottom surface. So
Steps are quasi-static.
Yeah, so they're small, and then, I mean, it's an experiment, so it's by definition quasi-static, you need to image it. This happens all over a time scale. Yes, very quasi-static. So I should say here that Jonathan Colmer spent rather a lot of time and about 15 pages of supplementary making certain that we can identify contacts accurately, which is the hardest bit of this. There's an accurate criterion for identifying contacts. Yeah. Yes, okay, it turns out that there are very few sliding contacts in here, and in fact, our original simulations were at really low friction coefficient, but there were many of these. So here it's a bit fuzzy exactly if a Coulomb criterion is appropriate for these, but there's only very few of these. So in whichever criterion you apply, it doesn't change anything substantially. That's also discussion of this in the supplementary. So it's.
But indeed, they're both pieces, they're not sliding because they use almost never normal.
Yeah, but so they could. Well, I mean, most of them indeed are equivalent to double bonds, so normal and tangential forces. So we've measured the tangential forces to check if there is evidence of an obvious Coulomb criterion, and that isn't really. So whichever way we define it, there is very few sliding contacts, and in fact, if I remove the whole idea of sliding contacts, this doesn't change substantially. So it's not sensitive to this, just exactly because there are so few of them in this type of experiment. How am I doing in time? It's not good, right? Yeah. So, okay, I'll quickly go through the rest. So I'm just saying, so you can correlate with these, and they correlate indeed very well. Ask me more if you're interested, yeah? And it still looks, with the caveat of this being an absolutely tiny system, like something compatible with the second order transition. So we still have a continuous distribution of cluster sizes. And the interesting bit here is you see the rigid cluster fraction as a function of contact number. In fact, hits 0.5 at 2.4. Yes, it needs including probability of spanning similarly at 2.37. So this is a number one does not usually hear with respect to jamming transitions. Yes, so the reason ours is so different, and I think, at least in my opinion, it's the more honest number to quote in something like this, is because we did not remove rattlers, because any algorithm of removing rattlers is, in a way, it's counterproductive to what we're doing with rigidity. Rigidity itself can tell you which part of your system is floppy, and which part of it is rigid. So, for example, this is uncorrected pressure as a function of contact number. This is without rattlers with a recursive algorithm, whereas if I use the rigid cluster, in fact, everything which remains is above 3 except for some very small subclusters. So this should be the correct way of identifying which parts of your system are rattler-like and which ones aren't. And in fact, you can look at the pressure again. The pressure inside my rigid cluster is always bigger than the pressure outside of my rigid cluster, and that's true. On an element-by-element basis, is true for every single rigid cluster in the system. We think mechanically, truly, there is something going on, and this is the correct way of decomposing it. Yeah, we can do new stuff, but I wanted to spend what little time I have on a couple of questions here. So one of them is, what if anything has this to do with shear jamming? Yeah. So one funny thing is, we actually did a correlation between the shear jamming rigid clusters, so based on the force chain thresholding, and our rigid clusters, and we found, using the statistical adjusted rand index, that the correlation was absolutely zero. So you have statistically zero correlation between force chains and our rigid clusters. So that's one of the things we don't understand. And the hypothesis now is that force transmission and rigidity are two completely different things, which don't actually have to correlate with each other. The other one is, and related to that, is how can I even have a rigid cluster like this? So in a system which is purely repulsive, if nothing around it here carries a force or a load, like how could I even have something like this? It can't possibly have positive pressure. So the answer here must come from the other forces in the system, which are always there, tiny viscous forces and forces to regions which are actually unstable, like through a shear band, for example, where that always happens. And in fact, Shrikant Shastri and his student have looked at this more recently with, I should say, much larger system sizes than us. They're looking in the limit where gamma dot going to 0, so the shear rate goes to 0, like more to 0 than we do. And in fact, he finds that the transition changes. So it's second order and it becomes more and more first order like as you really take this to 0. So something is happening when I'm changing the background of dissipative forces around there. And in fact, more to the point, one could do the same thing and say, could I link this to shear thickening in the end suspensions for roughly the same reasons? So just as a reminder, which I don't really need to do in this audience, the idea for shear thickening is that it's a switch from a frictionless to a frictional contact. As you go through the transition, you start with all of these lubricated contacts, and then eventually, if it stands enough, I hit them. I get frictional contacts, and you get a backbone of this frictional stuff, which then with a pretty sudden onset increases the rigidity of the system, and hence huge shear thickening. And so that, for example, here the linkage theory of this, original linkage theory here by Mathieu here from a couple of years ago is based on this. The question now is that if you have these possibly second order rigidity transition going on in there, does this have anything to do with this? And could one use tools like this to look at it? And I should say several groups are currently looking into this, and the current emerging consensus is that something indeed happens in this phase diagram, but exactly how linked or not linked is to the discontinuous shear thickening is still an open question, including in particular how one should deal with the hydrodynamic forces. Am I out of time?
We should take a little bit more because of the.
Then I would like to spend about the 2 minutes on the last piece of my talk I wanted to talk about, is that if you are dissatisfied by the system sizes and so on, which I showed you so far, we also looked at a lattice model of frictional rigidity percolation just to understand what's happening in here from a point of view of a field theoretical critical exponents and similar. So the idea here is that we don't care so much of force balance, we just want to understand if one can, by playing these games with alternating double and single bonds with free pebbles per particle, and decompose it into rigid clusters, what kind of is the nature of the transition in these models. So in fact, we find in this one actually this time unambiguously a second order transition, regardless of the model details. So if my connectivity is below a threshold of adding these single and double bonds, I have small rigid clusters. I have a spanning rigid cluster which emerges at a critical threshold. Then above, I have a system which is rigid. And with quite a bit of careful work and system size scaling and all of this, one can look at the exponents of these. And in fact, what we find is something interesting. So regardless of exactly how we do this, we find consistent critical exponents, in particular here for the correlation length exponent and the cluster size exponent, which are distinctly different from central force rigidity percolation. So from the rigidity percolation, you'd expect the classical one with bonds on the lattice corresponding to the 2-3 pebble game, and which again, already know that already, are different from the ones of connectivity percolation. So there's something different going on with this type of algorithm. And so in particular, Jen has some ideas for why this might be the case. So the question is, why is this different from standard percolation? And one of the ones is that there's a couple of things. You get very interesting rigid structures between clusters. You get something like rigid hinges. You can get a finite number of very specific configurations which can link one cluster to the other. So these are special, there's a finite number of them. And also that this is a non-local problem. So for example, in this system, if I add one extra miserable bond between here and here, yeah, the whole system goes from floppy, no spanning rigid cluster, to rigid here, including, as you can see over there, I added a piece of rigid cluster here, which is very far away from where I actually added the bond. So it's a non-local problem, which makes it different from usual percolation. So all in all, in conclusion, so I think frictional rigidity percolation is a new tool to understand frictional granular packings. And so we have evidence for non-mean field transition, both in experiment and in simulation. And it's very in contrast to frictionless jamming. So you really see using the same tools, these are different from each other. So this is also a different universality class in a lattice model from standard rigidity percolation. But a lot of this opens new questions, like, is there a link to discontinuous shear thickening? Because there should be, just based on the phenomenology of it. And also relatedly, what's the role of viscous forces in stabilizing these rigid clusters and on the order of the transition? And then also, what is the link to force transmission? Like, if anyone has any ideas, because I don't anymore at this point, I've stared at these sufficiently long. So I want to say, to be continued, here is again, here's the 3 papers I mentioned related to this. And I wanted to end with, again, acknowledging my collaborators.